Hello, welcome to the session 1 of week 1. We'll discuss about history of additive manufacturing in the first part, and later we'll delve into value additions of additive manufacturing. As we all know, additive manufacturing is also known as 3D printing. It uses computer aided design to build objects layer by layer. This is in contrast with traditional manufacturing such as solidification, deformation, and so on, where bulk materials are made, they are cut, and sometimes unwanted material is machined away from the solid piece of materials. A simple workflow of additive manufacturing is shown here. Let's say we want to make something. We need to think about, is additive manufacturing the only method using which the object can be made? Has the object got a very complicated geometry? If so, then additive manufacturing method is a good method using which it can be approached. We need to plan and think further. What is the final application? What material will be used to make it? And what are the dimensions? Once we know about all this, we can design it. We can make a CAD file and print it. Additive manufacturing has come a long way to become an integral part of current manufacturing industry. It is already being used to specific objects that were not easily made using traditional methods. As we have developed, the parts that we make, the components that we manufacture have become more complex. We want them to be more precise, and thus we want a better control. This chart shows on the x-axis time and on the y-axis complexity of the parts. By the end of 18th century, mechanical loom was introduced, and soon there was also steam engine. The first industrial revolution was driven by mechanical production facilities powered by water and steam. As the 20th century started, we also saw second industrial revolution, which was driven by mass production based on the division of labor powered by electrical energy. By 1950s, computers were introduced to industry. They were used for production and both for research. In 1973, ARPANET, which was the Advanced Research Projects Agency, which is currently called DARPA, had its research network of computers. It had only 30 nodes and probably was not sufficient to do decent amount of calculations in faster way. And that drove the introduction of electronics and IT for further automatization and production, and thus started the third industrial revolution. By 2020, there were 30 billion devices connected with the internet. It is expected that by 2025, there will be 75 billion devices connected to the internet. We are living through the fourth industrial revolution. We want our physical systems to be connected to the internet. We want them to be controlled. We want to use AI because we want better precision, as mentioned earlier. And thus, additive manufacturing is also expected to be controlled by AI. It is interesting to note that general concept and procedure to be used in 3D printing was first introduced by Murray Leinster. Murray Leinster was a scriptwriter, playwright, and a storyteller, and his real name was William Jenkins. In his 1945 short story, Things Pass By, published in a magazine called Thrilling Wonder Stories, he writes, "But this constructor is both efficient and flexible. I feed magnetronic plastics, the stuff they make houses and ships of nowadays, into this moving arm. It makes drawings in the air. Following drawings, it scans with photocells, but plastic comes out of the end of the drawing arm and hardens as it comes. Following drawings only. In 1971, Johannes Gottwald patented liquid metal recorder. A liquid metal recorder is nothing but it's a device which can print liquid metal using continuous inkjet on a substrate or a surface, and it can be either immediately used for printing or can be remelted for next use. This appears to be the first patent describing 3D printed, although in 1974 David Jones laid out the concept of 3D printing formally in an article that he published. 1980 to 84 was the period where some of the pioneering and fundamental work towards development of additive manufacturing happened. In 1980, Hideo Kodama of Nagoya Municipal Industrial Research Institute invented additive methods for fabricating 3D plastic models using photo-hardening thermoset polymers. He filed a patent for a device called XYZ plotter but could not gather enough support. In 1982, Raytheon Technology Corporation was granted a patent to make use of powdered metal with laser to make objects layer by layer. An American entrepreneur called Bill Masters filed a patent for automating manufacturing processes, and this technology was later used for additive manufacturing as well. Between 1983 to 84, Chuck Hull filed a patent for a stereolithography fabrication system and introduced the concept of creating objects by curing photopolymers. In 86, he started a company called 3D Systems Corporation, where the first commercial 3D printer SLA-1 was introduced. In 1988, Scott Crump developed fuse deposition modeling, a method which was used for thermoplastic material printing, and this gave rise to a company called Stratasys. Stratasys commercialized FDM technology and marketed its first FDM printer in 1992. Richard Helinsky in 1989 patented a method for constructing three-dimensional objects using particle deposition by using inkjet technology. Overall, 1980 to 90s saw emergence of key technologies of additive manufacturing, for example, stereolithography, fuse deposition modeling, and inkjet-based approach. In 1993, Emanuel Sachs introduced powder bed 3D printing with inkjet print heads at MIT. A company called Sanders Prototype was established, which was later called SolidScape. They began inkjet 3D printing with soluble support structures. In 1995, Fraunhofer Society developed the selective laser printing process. Now AM process started making inroads in the existing industry. They offered new object geometries of metals, more complicated topology, and there was more focus on materials and support structures. Overall, 1990s marked period of experimentation, exploration, and innovation in additive manufacturing. There were some development in new material deposition technologies also. For example, powder bed 3D printing with inkjet print heads. In 2009, fuse deposition modeling process patents expired, leading to commercial FDM 3D printers. There were new companies that were making affordable FDM printers now. By 2010, end-use parts like engine brackets and large nuts were being grown using additive manufacturing. Now AM started challenging traditional manufacturing methods, entering aviation industry. Overall, in the period of 2000 to 2010, AM focused on reduction of cost, printing of non-conforming parts, more complicated geometries, increase in fuel efficiency in jet engines, and integration of AM in aerospace. Companies like Airbus and Pratt and Whitney came in for interest in additive manufacturing. AM adoption grew significantly in versatile domains beyond aviation as well. In 2014, platform for multi-material vertically integrated printed electronics using additive manufacturing was demonstrated. This meant that now micro components using various materials could be printed on the same chip or at the same location of the board vertically. Printed prices further dropped, making this technology more accessible, and that aided to the evolution of additive manufacturing. In February 2015, GE received the FAA certification for its T25 sensor housing, which was their first AM part, and it was later used in G90 engines. Airbus received the first GE's LEAP engines, which were integrated with 3D printed fuel nozzles. These fuel nozzles demonstrated 25% weight reduction, reduced assembly times, and fewer parts. AM's potential for optimized design, printing of more complicated geometries, and weight reduction, rapid production was highlighted in aerospace. In the second half of 2010s to 2020s, metal additive manufacturing started making significant impact on aviation industry and beyond. This aided to cost reduction and improved efficiency of the manufacturing process. Metal additive manufacturing continued to expand in various sectors beyond aerospace. Defense, medical, automotive, they started adopting metal AM for specialized components. More complex geometries were made, lightweight structures were created, and rapid prototyping was happening, and these all drove the adoption of additive manufacturing. GE Aviation announced plans to use AM for mass production of large and complex parts. Now the industry targeted reducing lead times, improved energy efficiency of the manufacturing process, and minimizing waste. AM's applications diversified further. For example, customized medical implants, tooling, and high performance automotive parts. This was the time when application of AI and digital twins was also explored for additive manufacturing. By 2019, metal AM processes became more standardized and accessible. There were more material choices available for 3D printing. Continued growth of additive manufacturing led to its maturation and establishment of AM as a viable manufacturing method. Overall, in the period of 2015 to 20, there were many advancements in the form of integration of AM with traditional methods. There was emergence of AM in sectors like defense, automotive, and the adoption was mainly driven by creation of complex geometries, optimized designs, less iterations of better designs, reduction of waste, and so on. Also, there was usage of digital twin technology for better control and improvement of additive manufacturing. 2020s show significant democratization and diverse applications of 3D printing. Now this technology is more affordable and accessible. A polymer printer is available for under $200. There are diverse applications beyond engineering. For example, it is being used in medicine, architecture, art, and fashion. There have been significant technological advancements in AM. For examples, now we have improved software that control the AM machines. We have slicing algorithms which are better than earlier. We have advanced materials that can be printed. Now AM technology has been integrated with Industry 4. Now the AM is being developed as part of cyber physical systems. There is more customization and personalization. There is trend of producing personalized home decor, electronics and personalized accessories. AM has been introduced significantly to the education, especially higher education. Manpower is being trained. The 3D printing is integrated to curricula for design and prototyping. AM technology is now more focused on sustainability and eco-friendly practices. There is more usage of recycled materials. There is more focus on optimized material usage and reduction of waste. There have been significant medical breakthroughs because of additive manufacturing. For example, one can print patient-specific implants. Tissues can be printed and drug delivery systems can be printed, which were not possible earlier. There have been significant geopolitical implications also because of patent expiration, reduction of cost of additive manufacturing. The localized production has disrupted global supply chains and it has changed the manufacturing dynamics significantly. In 2020s, the 3D printing has become more accessible, versatile, impactful, and it spans engineering, education, medicine, and arts. The advancement in technology enhance capabilities, offering customization, sustainability, and innovation. Thank you to listening to this part of session 1. We'll see you in the next part, which focuses on value addition due to additive manufacturing.